This video will show an example of a truss. First of all, analyzed by hand calculations and also using robot structural analysis program. Truss has a pin support, a roller support, a vertical load, and a horizontal load. Dimensions are 3 and the height of the truss is 4 meters. And the joints are A, B, C, D and E. First step will be to calculate the reactions. For this we will write sum of horizontal forces is 0, sum of vertical and sum of moments about point A equal to 0. And for the vertical, at pin support we have VA, at roller support VC, and at pin support we also have HA. Horizontal forces are HA plus 40 equals 0, assuming positive forces acting to the right. Assuming positive forces acting up, VA plus VC minus 50 equals 0. The moment equation will assume positive moment as clockwise, and about A, force of 40 is at a distance of 4, and force of 50 is at a distance of 12, and both are positive as they are turning clockwise. Minus VC times 6 anticlockwise equals 0. From this last equation, VC is equal 160 and 760 divided by 6. Is 127 kilonewton, rounding to the whole number. And from the second equation, VA is equal to 50 minus 127, which is equal to minus 77 kilonewtons. Therefore, VA is downward force, and HA is minus 40 acting to the left. Next, we will need to find the angle. The angles to the horizontal are all equal to theta. And the triangle that we are looking at is 3, 4, and so theta can be found as tan inverse of 4 over 3. So cos theta equals 0.6 and sine theta equals 0.8. you can calculate this angle. I will draw the truss again. And the reactions, this one is 77, 40, 50, 40, and 127. We can start with the equilibrium of either joint A or joint E, because we can't start from the joint where there are three members, because that would be needing three equations, or in this case 4 unknown members. So B, C and D are impossible to start with. We have to start from either joint A or joint E. So if I start from joint A and remove this joint from the truss and look at the equilibrium of forces in the joint, at joint A there is a downward force of 77, 40, and in the members that are cut are the unknown forces pulling away from the joint. So this one is FAC and this one is FAB. Writing the sum of forces horizontal at this joint, angle theta, taking positive forces to the right, 40 minus 40 plus FAC plus FAB cos theta equals 0. In the vertical direction, minus 77 plus FAB sine theta equals 0. The force, which is neither horizontal nor vertical, has a horizontal component, the force multiplied by cos, and the vertical force multiplied by sine. From the second equation, FAB equals 77 over sine theta, which is 0.8. 8 equals 96 kilonewton, and it is positive, which means tension. From the first equation, FAC equals 40 minus FAB cos theta. It's equal to 40 minus 96 times 0.6. Which is minus 18. Therefore, FAC is in compression. This was joint A. Next one we can consider would be joint B. Now, removing joint B, we are cutting members FAB, FBC and FBD, but now we already know FAB, so we only have two unknown members, so we can consider this joint. FB. So this is the force FBD, and this is the force FBC, and here would be the force FAB, which we found is 96, and because it is tension, we draw it away from the joint. Sum of horizontal forces at the joint B equals 0. FBD minus 96 cos theta, cos because horizontal, plus FBC cos theta equals 0. Sum of vertical forces equals 0. Minus 96 sine theta minus FBC sine theta equals 0. Again, we have two equations. We can find these two unknown forces from the second equation. FBC equals minus 96 sine theta divided by sine theta. It's equal to minus 96 kilonewtons. FBC is in compression. From the first equation, FBD equals 96 cos theta plus FBC minus FBC cos theta. It's equal to 96 times 0.6 minus FBC is minus 96 cos theta. Instead of cos theta, I'll write 0.6. And that is equal to 96 115, and this is positive, therefore tension. The next joint we can consider is either C or D or B or E, because in each of them we now have two unknown forces. Let's consider joint C. In joint C, there are four forces, four members, that are cut, and also there is a vertical force of 127. These forces are unknown, FCD and FCE. The angle is theta, and force FBC is minus 96. 96 compression. No need to put any sign, just to direct it in the correct way, to compression towards a joint. And 115 FAC was minus 18. Also compression, so also towards the joint. Sum of horizontal forces is 0. We'll give 18 plus 96 cos theta plus FCD cos theta plus FCE equals 0. Sum of vertical forces is 0, will give 127 minus 96 sine theta plus FCD sine theta equals 0. From this is equation 1 and 2. From equation 2, FCD equals minus 127 plus 96 times 0.8 divided by 0.8 so it's 127 negative 127 plus 96 times 0.8 divided by 0.8, and that is minus 63, which means this force is compression. And then from the first equation, FCE equals minus 18 minus 96 times 0.6 and plus minus FCD cos theta. So FCE equals minus 18 minus 96 times 0.6 FCD is minus 63, so this is minus 63 times 0.6, which is equal minus 18 minus 96 times 0.6 plus 63 times 0.6 equals minus 38. Compression as well. And now the last force to find is FDE, and for this we can either look at equilibrium of joint D or joint E. If we look at equilibrium of joint E, at joint E we have the force of 50. This is the force FCE, which we found as minus 38, and this is the force FD, which we need to find. From sum of horizontal or sum of vertical forces equals 0, sum horizontal forces equals 0, 38 minus FDE cos theta equals 0, therefore FDE equals 38 divided by 0.6, and that is 63, and that is in tension. So we have found all the forces in the truss. A, B, C, D, E, 50, 40, 1 to 7, 77, 1 to 7, and the forces that we calculated. FDE is tension. It is shown like this, 63. FCE is compression, 38. FCD is compression 63. FBD is tension 115. FBC is 96 compression. FAB is 96 tension. And FAC is 18 compression. Now we can try to analyze this truss also in robust structural analysis and compare the findings. For the cross section, we can take perhaps solid section 100 by 100 from S275 steel. Opening robot structural analysis, new project, and for the truss we can use Truss 2D type file. We start with the nodes and using the screen we can place the nodes, first one at 0, 0, then at zero, first node at 0, 0, second node at 3, 0, third node 6, 0, third node at 12, 0, fourth node at 3, 4, and fifth node at 9, 4. And going to next sections. For the section we'll choose the new section, sections. For the section we can choose the new section, parametric, solid, 100 by 100, and I will rename it 100 by 100. And next we can go to the bars, and for the bars, simple bars, correct section, place the bar from node 1 to 4 to 2, 2 to 5, 5 to 3. So we place all the bars and go to the next step, which is supports. I have already created a roller support, so I can put the pin support at 1 and roller support at 2. And lastly, going back to bars, I've forgotten to put top bar. And lastly, loads. Dead load will just contain the self weight, and live load will be specified. In the x direction the force will be 40 positive, and it's acting at this node, and at and the vertical force of 50 is applied to this node, not 50 but minus 50. So I can just change it to minus 50. And that is pretty much it. The forces are applied, and I can do the calculations. And next will be to look at the results. So first I will check the reactions. Descriptions all apply. So changing to the live load. Why do I not have live load? Going back to the loads. It seems that I have applied both as dead load, so I can correct that. Apparently I haven't created a live load case. Live load, add. Yes. Fine. So now I can change this. Okay. A live load, okay, and then I will recalculate. So now I will go back to the results and apply. The reactions for live load are 77 down and 127 up, and the horizontal is minus 40. Next I can have a look at the hide the reactions and show the axial force diagrams. Apply, and to see the values I will click on labels, differentiated field. So this is showing me the forces, which are 18, 96, minus 96. So this positive force in a robot means compression. So this member has compression, tension. Purple ones are all compression and yellow ones are in tension. And we can check all the forces if they are correct. Also we can view the forces. For example, if we can't see for this member clearly what the force is. If we select it, then we can choose the force for this member. So it is for the load case 2, it is 62.5, and so we can also hide the diagrams and show the stresses. This is the stress in megapascals in all members, and we can also show the deformation, so we can visualize how the frame deforms. And the maximum displacement is 2 millimeters from the live load case. Right, so this is all for this example.